Assalamualaikum and hi everyone. In this video, we are going to learn about chemical bonding. Alright, in this chapter 4, there are 5 subtopics. 4.1 is Lewis structure, 4.2 is molecular shape and polarity, 4.3 hybridizations and orbital overlap, 4.4 intermolecular forces, and 4.5 is metallic bond. Okay, so let's start with Lewis structure. At the end of the lesson, you should be able to write the Lewis symbol for an atom, state the octet rule, and describe how atoms obtain the octet configuration. Describe the formations of the following bonds using Lewis symbol, that is ionic or electrovalent bond, covalent bond, dative or coordinate bond. And the next learning outcome is to be able to draw Lewis structure of covalent species with single, double and triple bonds. And the last one is to compare the bond length between single, double and triple bonds. Alright. When atoms interact to form a chemical bond, only electrons in the outermost or valence shell are involved. And this electron, we call them as valence electron. For group 1, the valence electronic configurations in general is NS1, and that means the number of valence electron in group 1 is 1. For group 2, the electronic configurations in NS2, and that gives the number of valence electron is 2. Group 13 is NS2 and P1, and that means the number of valence electron is equal to 3. Group 14, NS2 and P2, and the number of valence electron is 4. Group 15, NS2 and P3, so the number of valence electron is 5. Group 16, NS2 and P4, and the valence electron is 6. Group 17, NS2 and P5, and the number of valence electron is 7. Alright, now let's look at the Lewis dot symbol. Okay, Lewis dot symbol is a symbol in which dots or crosses are used around an atomic symbol of an element representing its valence electron. Okay, for example, the electronic configurations of oxygen is 1s2, 2s2, 2p4. So the number of valence electron is 6. Since there are 6 valence electrons in oxygen, that means there are 6 dots around the oxygen symbol. So in order to draw the Lewis dot symbol, firstly we draw the symbol of oxygen, that is O, and then there are 6 dots around the oxygen symbol. Okay, so don't just put the dot anywhere. Okay, the dot should be neatly drawn on the 4 sides around the element, and no more than 2 dots at each side. So here we can look at the Lewis dot symbol for all groups in the periodic table except for transition metal. Okay, so for group 1, since atoms in group 1 has the same valence electron, that is 1, so that means there are only 1 dots that represent the valence electron. For group 2, there are 2 valence electron, so there are 2 dots around the atom. And then for group 13, there are 3 valence electrons, so there are 3 dots around the atoms, and group 14, 15, 16, 17 and 18, it has the dots that represent the valence electron. But except for helium, since helium has 2 electrons, so it has only 2 dots around the helium, even though helium is in group 18. Okay. Octet rule. Octet rule states that atoms lose, gain or share electrons in order to have a filled valence shell of 8 electrons. Atom can achieve noble gas or octet configuration through transfer of electrons or sharing of electron. Hydrogen and helium is excluded because it can hold a maximum of 2 electrons or duplet in its valence shell. And noble gas from group 18, elements exist as monoatomic gases and not need to bond to other atoms as it is already stable. Okay, now let's look at the type of stability of electronic configuration. Electrons in the valence orbital can be removed or added to form cation and anion in order to have stable electronic configurations due to the following: noble gas configurations, pseudo-noble gas configurations, and stability of the half-filled orbital. Okay. Noble gas configurations, group 1, 2 and 13 elements donate valence electrons to form cation with noble gas configuration. For example, sodium, it has 11 electrons in total. That is 1s2, 2s2, 2p6, 3s1. So in order to form cation or positive ion, electron from 3s will be removed and it gives Na plus with the electronic configuration of 1s2, 2s2, 2p6. A group 15, 16 and 17 elements accept electron to form anion with noble gas configuration. For example, oxygen, the electronic configurations of oxygen is 1s2, 2s2, 2p4. In order to form anion, it will gain another 2 extra electron, and the anion is O2 minus, and the electronic configurations for O2 minus is 1s2, 2s2, 2p6. So in general, the valence electronic configuration of noble gas configuration is ns2 and p6. This electronic configurations is equivalent to the noble gas electronic configurations. Okay, next, let's look at the pseudo-noble gas configuration. Electronic configurations in which all the orbitals are fully filled with electrons. Okay, so that is what's the pseudo-noble gas configuration mean. But even though the orbital has fully filled electrons, but they are not that of any of the noble gas. The valence electronic configuration is either ns2 and p6 and d10, or ns2 and p6 and d10 and f14. For d block elements, electrons from 4s orbital will be removed first before the 3d electrons. For example, zinc. zinc has 30 electrons that give the electronic configuration 1s2 to s2, 2p6, 3s2, 3p6, 3d10, 4s2. So what's happened here? The electron from 4s orbital will be removed to form zinc 2 plus, and the new electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Okay, so the valence electronic configuration here is 3s2, 3p6, 3d10. These orbitals are all fully filled with electrons, but its electronic configurations is not equivalent to any noble gas. So we call this as pseudo-noble gas configuration. The last one is stability of half-filled orbital. Okay, in block D, all the elements can also donate or receive electrons to achieve half-filled orbital which is stable. For example, manganese. Manganese is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2. So in order to achieve half-filled orbital, electron from 4s is removed to gain the new electronic configurations 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. 3d5 here is a half-filled 3d orbital that is more stable compared to the original electronic configurations. So Mn2 plus is the stable ion for Mn.